Before we get started, a quick disclaimer. Everything in this video is for educational purposes only. Do not use these techniques on real websites, networks, apps, accounts, or devices unless you have explicit written permission. With that out of the way, let's get on with the video. Right, okay, welcome back. In the last couple of SQL injection videos, we looked at how vulnerable applications can be tricked into showing hidden data, and how SQL injection can sometimes be used to bypass authentication. This time we're going a step further. We're going to be looking at SQL injection union attacks. And this is where SQL injection started to feel a lot more powerful to me, because instead of just changing the logic of the original query, we can potentially use that query to pull data from somewhere else in the database, which is slightly terrifying, but also really useful to understand if you're a developer and you want to know how to defend against it, which we'll get onto another point in time. So what is a union attack? Well, in SQL, the union keyword lets you combine the results of two select queries. For example, you might have something like this: select AB from table 1, union, select CD from table 2. In plain English, that means get column A and column B from table 1, then also get column C and column D from table 2. Then combine those results together into a single result set. So the final response still has two columns. The first column, though, contains values from A and C, and the second column contains values from B and D. And that's the important part. Union lets us add another select query and append its results to the original query. Now, for that to work, there are two key rules. Rule 1. Both queries must return the same number of columns. So if the original query returns 3 columns, our injected union query also needs to return 3 columns. Rule 2. The data types in each column need to be compatible. So if the original query expects a number in the first column and we try to put a string in there, the database might complain. That means before we can do anything useful, we need to answer two questions. Firstly, how many columns does the original query return? Secondly, which of those columns can hold the type of data that we want to extract? Now, most of the time, the interesting data we want to test with is string data. So things like usernames, passwords, email addresses, names, or other text values. So we're mainly looking for columns that can handle string types like varchar, text, blob, or similar things like that. So how do we find the number of columns first? Well, there are two ways. The first method is using order by. So we can inject a series of order by clauses and keep increasing the column number. So for example, you do a single quote, order by 1, dash dash. Then we can do a single quote, order by 2, dash dash. Then single quote, order by 3, dash dash, and so on and so forth. What we're doing here is asking the database to order the results by a particular column number. We don't need to know the column name. We're just saying order by column 1, order by column 2, order by column 3, and eventually we'll ask it to order by a column that doesn't exist. And at that point, the application might throw us an error. So we might have something in the order of, the order by position number 3 is out of range of the number of items in the select list. You might see that error directly on the page, or you might see it in the HTTP response. You might see it in the browser console even. Or the application might just give you something generic. Sometimes it might not show anything at all. But any change in behavior whatsoever can be a clue that it's working or something's going on behind the scenes. The second method is using union select with null values. So we might try something like this: single quote, union select, null, dash dash. Then we might try single quote, union select, null, comma, null, dash dash. And then single quote, union select, null, comma, null, dash dash. Sounds like it's getting a bit of a rhythm there. And we keep going until the number of null values matches the number of columns in the original query. If the number doesn't match, the database or the application may throw an error. So the database error could be something like all queries combined using a union, intersect, or except operator must have an equal number of expressions in their target lists. It's very catchy. Database errors are basically poetry, if poetry hated you. So why are we using null? Null is useful here because it can usually be converted to common SQL data types. That means it gives our test payload the best chance of working once the column count is correct. When the number of null values does match, the database returns an extra row containing null values in each column. How that appears on the page depends on how the application handles the result. it might show an extra blank row, it might show an error, it might show some weird empty null pointer exception, or it might just look exactly the same, in which case that makes this method less useful. But in these labs, we are going to get something visible. So I'm going to jump straight into the PortSwigger Web Security Academy lab, where we've got that vulnerable shopping application. So let's go into there now. Let's access the lab. Okay, so let's just jump into the PortSwigger Web Security Academy lab. We've got the vulnerable shopping application again. We've got a list of products and a list of prices and a view details button on each row. We can also filter the categories like this. So when we click a category, the page changes. More importantly, the URL changes. We can see that query string that we like. So category equals gifts. So you see up here, question mark category equals gifts. And if that category value is being passed into an SQL where clause, and the application doesn't handle it safely, we might be able to inject into it. So for this lab, we're going to use the union select null method, union select null dash dash. So we'll try one null first, and we see that fails. So it tells us the original query returns more than one column. So let's try two null values and see what happens. Again, still nothing. So I'll try three null values. Let's just put another one at the end here. If I can spell null correctly. This time, success. So the page returns properly. The lab recognizes we've solved that part, and you can see there's an extra empty row at the bottom of the table. It's hard to see on my screen, though. So that tells the original SQL query returns 3 columns. So we are getting somewhere, but we're not done yet. Knowing the number of columns is only the first part. Now we need to know which columns can contain useful data. Specifically, which columns can handle string data. So to test that, we're going to jump onto another lab and get to this same section. So here's the next lab, and to test that, we're going to take our successful union select payload and replace one null at a time with a test string. So here it wants us to use the string JROHHK. So what we're going to do, we've got 3 columns, so we're going to try the first one. So we change the first null into a single quote with that string, if it will paste it. No, it didn't paste it. So let's just do a copy, and we'll go back here, paste. Yep, there we go. And we get an error. Okay, so that's not it. Let's make that the second column then. Do that, and boom. So there we go. So now we've got the compatible column is the second column. So you saw there before that if the column is not compatible with string data, we get an error. So in this case, it was a generic internal server error, but you might get something like a database error saying conversion failed when converting the varchar value to type int, something like that. That would actually be useful because it tells us that the column probably expects a number. But if there is no error and the string appears somewhere in the response, like it did here, then we know that the column can handle string data. So in this lab, we use the random string that was generated by PortSwigger. In this case, it was JROHHK. We put that into each column, and we found out that it was the second column that is compatible with strings. Now, I could also try that on the third column, and if we did do that, let's just stick in an A here, and we get the internal server error again. So nope, that one errors out as well. So for this lab, we know 3 things. The original query returns 3 columns. The first column is not useful for string data, second column is string compatible, and the third column is not useful for string data. So that means if we want to extract text from somewhere else in the database, the second column is where we're going to need to put it. Now, let's take a look at retrieving more interesting data. So in the next example, the lab tells us there is a table called users, and that table has 2 columns. It has username and password. In a real situation, you would not normally just magically know that. You need to inspect or enumerate the database structure, and different databases expose that information in different ways. But that's outside the scope of this lesson. For now, the lab gives us a table and column names so we can focus on the union attack itself. Back in the lab, we'll start by doing the same process again. So we've got this page here, and we can start by doing a union select with increasing number of null values. In this case, I know that this returns 2 columns. So we know it returns 2 because if we scroll down here, we can see it just barely. There's an empty thing down there. So then we can start swapping them out for strings to see which ones do strings. So that contains a string. And what about the next one? That also contains. Okay, so we know that in this case, we discovered the original query returns 2 columns and both of them can handle strings. That's perfect. Because if there are 2 columns available and both can handle strings, we can ask the database for usernames and passwords from the user table. So the payload for that would look something like this. So we do single quote union select plus boom, 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 username, comma, password from users dash dash. And what that does, sends another select query to the original, and instead of just returning products, we're now asking for usernames and passwords from the users table. And because the page displays the results, you've got those values dumped into the HTML. So run it, it works, and the page now includes extra entries where the username appears in bold and the password is just underneath it. And at this point, you'd hope that those are not real passwords. Surely the application has not stored passwords as plain text in the database, right? Let's copy that one and go to my account. Let's type administrator and put his password in there and log in. Yeah, that works. In a real application, that would be a serious security issue. An attacker could access an account they should never have been able to use. And if that account has admin access, the damage could be much, much worse. Now, what happens if we only have one string-compatible column? Because in the earlier lab, only one of the columns could handle string data, if you remember. What if you wanted to extract both username and password, but only have one useful place to display the text? The answer is concatenation. Concatenation is just a fancy word for joining things together. So instead of putting the username in one column and the password in another column, we join them together into one string. For example, we might see something like this. Username, double pipe, tilde, double pipe, password. In some databases, the double pipe symbol is used to concatenate strings. It means join the username, then add a separator, then the password. So the separator is important. If we just smash the values together, they might be hard to read. So we use something like a tilde between them or a dash or something like that. That way, the output might look like something like administrator, tilde, some password. So different databases use different syntax for string concatenation. So this exact version won't work everywhere, but the idea is the same. Join multiple values together so they can be returned inside the column. So back in the lab, we find that the original query returns 2 columns, as you can see. But in this one, only the second column will actually return string data. So our injected query still needs to return 2 columns. But for the first one, we can use null. And for the second one, we will concatenate the username and a password. So the payload will look like this. Single quote, union select null, username, double pipe, tilde, double pipe, password from users dash dash. Okay. So the null keeps the column count correct. The concatenated username and password go into the string-compatible column, and then when we send the request, the page should display the data. Boom! We can see the usernames and passwords joined together with the tilde separator in between them, so we know where that gap is going to be. And once again, we can double-click and copy the administrator password, go to My Account, type in administrator, paste the password, and boom. Yikes, because this is exactly why SQL injection is such a serious issue. In the earlier labs, we just changed the logic of the original query and made some hidden products appear. We bypassed the logic check, which is pretty serious. But with union-based SQL injection, we're using the original query as a doorway into other parts of the database. So that means an attacker may be able to extract information that was never meant to appear on that page. Customer records, email addresses, account details, admin credentials, credit card numbers, internal notes, anything that the database user can access could potentially become exposed. So from a developer's point of view, what do we learn from this? Well, the biggest lesson is that user input should never be stitched directly into SQL queries. If you build SQL by joining strings together, you're giving user input the chance to change the structure of the query, and that's exactly the problem. Now, some of you would say that a query string is not user input, but anything that the user can tamper with is technically an input for them. Applications should use parameterized queries or prepared statements. We'll get onto that in another future video, but the SQL structure should be defined by the application. The user input should only be treated as data, not executable SQL logic. On top of that, you want strict server-side validation, careful error handling, least privileged database accounts, and you definitely do not want to store passwords in plain text. Hopefully that one goes without saying, but apparently not in this lab. For me, union attacks were the point where SQL injection really clicked. Column count matters, data type compatibility matters. And once those two things line up, an attacker may be able to pull data from completely different tables. That is both fascinating and horrifying, which is basically the cybersecurity learning journey in a nutshell. As always, this was carried out in a legal training lab using an intentionally vulnerable application. Do not test these techniques against real websites, applications, databases, or accounts unless you have explicit written permission to do so. Anyway, next up, I'm going to start looking at how attackers can discover database structure, including how different database engines expose information about tables and columns. So that's all for this video. If you like to hit the like button, do a thumbs up, hit the bell, subscribe, all the other things, comment, I don't know. If there's anything I've missed or you don't understand, comment below. I will go through all the comments and I will try to answer as many questions or explain things as best as I can down there in the comments section. But yeah, if you do like, comment, subscribe, that would be fantastic. And thank you very much for watching this video. Until the next time, until the next video, catch you later. Bye-bye.